Now that we've got all this moisture in the air, we've got to do something with it. Each of you is familiar with looking at clouds, I'm sure, feeling precipitation. So that's what we're going to deal with. We're going to take that moisture and we're going to do something with it, either form clouds, form precipitation. And you got to understand, this is not just a simple, oh, it reached a relative humidity of 100% of cloud forms. Unfortunately, it's a little more complex than that. So let's take a look at that this week. So water vapor is invisible. And clouds, on the other hand, are a visible part of water. When they form condensation, it gets wet. You can see dew on the ground, so you can see droplets in the clouds. However, there's also other aspects to clouds, such as cloud condensation nuclei. And these are very important into why clouds form. Cloud condensation nuclei can things, particularly in the Midwest, could be dirt off the ground, the type of dirt. Around my house, it's sea spray, forest fires. All different kind of things can be it. Even exhaust from chimneys and all can generate condensation nuclei. So let's take a look at a cloud droplet. First things first, I want you to understand the scale here. A cloud condensation nuclei is 0.2 microns. And the beginning of a cloud droplet is 20. So it's two orders of magnitude bigger than that condensation nuclei. So the condensation nuclei, that's why you don't see them. They're really tiny. They're dust in the air. The very initial drop is very, very small. Think about how tiny that is. An actual raindrop that you can see is 2,000 microns or 2 millimeters. So each one is 2 orders of magnitude bigger than the other. So some things happen when you get a cloud droplet that's so tiny. First off, it has a lot of curve. Think about it, a cloud top may not be perfectly round, but it has a curved shape. That curve means that the saturation vapor pressure around it, in order to keep the water condensation equal, must be much, much higher than over a flat water surface. We've been all the assumptions, everything we've talked about has been if the water was flat. Now, kinetic energy in curved droplet will make it extremely difficult for saturation to occur. So it is, if you don't have something else, the curvature effect will always keep clouds from forming unless the relative humidity might be up to maybe 200 to 300%, and that's just not going to happen. So what are these cloud condensation nuclei? Well, they're tiny little nuclei that actually dissolve in the water to form a solution. And that solution changes that water so that that water can hold in place, can take a cloud droplet. So without this hygroscopic nuclei, condensation nuclei, you cannot have water droplets in clouds. So if we had a perfectly clean earth, which we don't, never had, we would never have any clouds. And it depends on where you are as to what that condensation nuclei is. But that is the key to forming a cloud droplet. Everything, when it dissolves, it allows that water droplet to remain. It basically brings the relative humidity, the saturation vapor pressure, back down to where we used to talking about it. RH around near 100%. Now, when you go up in the cloud, obviously the temperature gets colder. So you'd say, ice forms, right? Unfortunately, that's not the case either. In order to freeze a cloud droplet, because they're so small and they have so much kinetic energy within them, you need to drop the temperatures way, way, way down. well below freezing. So most cloud droplets that you look up in a cloud at, many of them that are liquid or supercooled are below 0 degrees Celsius. So cloud droplets do occur. And again, we have ice forming nuclei. So we have another type of nuclei, and some of it again is dust particles or salt or different things like that, that will allow these tiny droplets to freeze. Some of them even go directly from water vapor to ice, depending on the nuclei. And notice that they become active at temperatures less than minus 9 degrees Celsius. So you don't have ice in a cloud very likely until you get a temperature in that cloud of at least minus 9. Now, in the wintertime, that could be pretty low to the ground. But in the summertime, that's getting up there in the clouds. And the other one, you don't actually go directly to ice unless the temperature is way up, down to all of less than minus 20 degrees. So again, it is very difficult to get ice in a cloud. But once it starts, it's kind of a key thing to have ice because that's what's going to cause your precipitation. So we know that supercooling water does exist, and it's because of the kinetic energy inhibits the growth of ice embryos to critical size. So what is precipitation? Precipitation is basically a cloud droplet got big enough that gravity pulls it to the earth, and it reaches a terminal velocity where there's friction with the air that slows it down to a certain point. But when it comes in equilibrium, the air's resistance and gravity, that's the terminal velocity of a water droplet or an ice crystal with snowflake. They're both different. So, and maybe if you have hail, it would even be different. So depending on what the size of the droplet is and what the consistency of that droplet is, you have different terminal velocities, the speed at which they're hitting the ground. So what causes precipitation? Now there's two processes. Basic one, collision coalescence, occurs in warm clouds. Guess what? We don't have a lot of warm clouds up here in the northern hemisphere. Most of our clouds are below freezing when we get up to our elevation. In the summertime, every once in a while you can get warm cloud precipitation. But most of our clouds to form precipitation use the Bergeron-Findyson process. So if you had a warm process, all you would need is a droplet just continues to grow. It gets big enough to start to drop and it hits other droplets and just sucks them in and gets bigger and bigger until it finally just reaches a velocity a weight that it will allow to come to the ground. They can make some pretty large raindrops this way. And when the water is that thick, and we know warmer air can hold more water, so obviously more water is available in a warm cloud than in a cold cloud. So warm cloud droplets can actually be a great way to get very heavy rainfall. That's why down in the tropics you get very strong, very heavy rain from the warm cloud processes there. You just don't get that much up here in the northern mid-latitudes. Bergeron, on the other hand, a little different, a little trickier. You need cloud temperatures. Obviously, you need to have ice in the cloud. So typically, you got to go below minus 9 degrees to get that first off. And at that temperature, water molecules are more readily to vaporize than an ice crystal. A solid molecule doesn't have as much kinetic energy as a liquid. So saturation vapor pressure over ice crystals is lower than over water. So guess where the water is going to flow to? The liquid is going to flow into those ice crystals. So the ice crystals are going to grow, and once they're there, they're going to dominate, and eventually everything will become ice crystals, even at a minus 7 or minus 8 temperature. Because once you get the first ice crystal, the process of Bergeron-Findyson says everything is going to eventually change to ice crystals. So now you have snowflakes, which have grown because all the liquid that was in the cloud condenses on the snowflakes and makes them big enough that they actually begin to fall. So here is one of the other things that goes along with that. When you get out of the base of the clouds, obviously the air is drier because you don't have condensation occurring there. And if it's a long distance down to the earth, you might get this virga. All that is these precipitation falling through drier air and evaporating. So that could cool the air underneath it. Maybe, and eventually, maybe it will make it get all the way to the ground. Maybe it won't. So, but it is something to look at here with these. All of it depends on the distance to the Earth's surface from the base of the cloud, and the lower the relative humidity air is beneath the clouds. So here's some different types of precipitation. Rain, drizzle's very tiny. Drizzle will almost always come out of the lower level and be a collision coalescent process. And it's coming out of the lowest level of a cloud. So when you get freezing drizzle in the wintertime, and there's been a lot of that around here lately, that freezing drizzle is forming in the lowest couple thousand meters of the cloud. Even though the temperature may be below freezing in the cloud, it's not cold enough for ice. You have that super cooled ice, water droplets. So that's where the drizzle is forming. Ice crystals, snow. Notice they're all different shapes. If you're forecasting snowfall at your location, one of the interesting things is look at these different shapes, and their sizes vary. Dendrite snow things are much, much bigger than these ice grams or whatever, or thin plates. So it really depends on the temperature of the atmosphere as to how much snow you may get. Say your snow was all forming minus 30 or below, would be very tiny particles and may not accumulate that much because it kind of compacts more. Whereas dendrites, on the other hand, are big, fluffy flakes of snow. They don't compact as much. So one case, if you had 1/10 of an inch of precipitation, you might get almost an inch or inch and a half of snowfall. Whereas with non-dendrites, you might not even get a half inch. So the type of crystal plays a role in how much snowfall you're going to get. Here's where the different forms of precipitation occur. We had this in the Midwest, in the East this last week. Temperatures would be above freezing in a part of the cloud. The bigger that layer is, and it doesn't take a big layer to get above freezing, to melt the snow that developed in the cloud, it becomes rain. Super cold rain maybe, but it becomes rain. And eventually, if it's warm enough all the way to the surface, it stays rain. If there's a little tiny layer, maybe the little layer at 30 or 31 degrees, that rain is going to freeze, especially if it's like 33 or 34 up here and melted the snow, it's going to freeze quickly. And if you have a bigger layer, it forms sleet. And finally, if it stayed cold enough all the way through, maybe just got just a touch above freezing at some point, you get snow all the way down. So this is something we look at as a meteorologist in the atmosphere to determine the type of precipitation. How much? I showed you it in an earlier storm you all had, where you could really see that type of precipitation occurring. Here's freezing drizzle, just the very lowest layer. The atmosphere can create a great glaze, though. So how do we detect precipitation? Radar. It's radio detection and ranging. All it is sending microwave signals out. And some people get concerned that they're really seeing a huge amount of radiation coming out of radars. Well, guess what? The total amount of radiation that comes out of a radar, if you were standing down on the ground next to it, is less than you would receive if you stood by a microwave. So what happens is, yes, those microwave signals go out, but the radar is a great listener. It actually listens a whole lot more than it actually sends these microwaves out because we're trying to hear where they went. We want that pulse to come back. And the two main modes of radar are reflectivity and velocity mode. Velocity is using Doppler techniques to determine what the air motion is somewhere. Here's the dome. And yes, it's a wonderful time to climb up those steps. I've done it. And I don't like heights. And inside the dome, you have a big antenna that rotates around. The dome basically is protecting it. And you can see the Doppler shift here. What that allows you to do is determine the motion of the particles. And here's the velocity radar on the right and reflectivity on the left. And you can actually see a red and a very light green next to each other in radar velocity. The light green is towards the radar, the red is away from the radar. So what that means is there's rotation right in that little tiny area. Rotation indicates possibly a tornado. And you can see it in the way of almost like a hook echo. And we're going to talk about hook echoes more later in the course, but you actually can pick them out on radar. And unfortunately, not every one of these hook echoes forms a tornado. And finally, you see down at the bottom something that comes from dual pole radar. Dual pole radar is at every National Weather Service and FAA radar now. It allows the shape of the raindrops to be detected, or the shape of the dust, if there's dust in the air, or bugs. Because believe it or not, radar can detect bugs. Here's a hurricane coming in. Using dual pole, you can actually see the amount of distribution of precipitation better. You get better estimates because you're determining the size of the rainfall. Phased array is another radar that may eventually come. Unfortunately, it costs about $1 billion a radar, and the government has made the decision that that's just way too expensive. And I understand that. I got the privilege of playing with one out in Norman, Oklahoma, looking at a tornado and at some hail events out there, as I was part of a team that was looking at new technologies at the time. Phased array is awesome radar. It can detect a tornado much faster than anything we have now, and with much more accuracy. And it can look at the idea of hail much quicker. So that, yes, we would probably be able to gain a few minutes of warning lead time with a phased array, but is it enough to justify that kind of cost? And that's the argument that goes back and forth every year as to whether we ever get any of these. Here's rainfall estimates. 5 days from, you can see tremendous rainfall in this storm, very tropical. One of the interesting things is that now with phased array, the rainfall estimates have gotten better. Not phased array, but dual pole. Cloud classification. Cirrus, wispy, frozen up at the very top, stratiform or layers, and cumuliform or heaped up or puffy. And you can know cloud, cold, warm, cold clouds. And here's some cloud streets coming off the Great Lakes. We talked about it when you talked about Lake Superior this past week and how the vapor pressure changed and temperatures. That is what forms these cloud streaks. Notice there's no precipitation, no clouds on the direction where the wind is coming from up here, but there sure is down below there. So that's the cloud streak and how they form with moisture coming off the water. And this is Doppler radar currently at Cleveland. What I wanted to show here, though, is just look at dual pole for a minute and use it to identify hail. There's something called differential reflectivity. Basically, it is looking at the change in shape of a parcel. So if all the parcels around it are the same shape, which would happen in a rain, they're pretty close to the same shape, they would look one way. But when you get hail, that's a whole different shape. It can be all kind of different formations to hail. And it stands out on differential reflectivity. And you get an idea that there's very strong reflectivity returns on base reflectivity. But with differential, you can actually pick it out. So hail is very nice to be detected on dual pole radar. And let's see if we can get anything here. If not, I'm not going to worry about this too much. And it's not a lot right now going on. There was a little bit on Cleveland earlier I was trying to look at. And there it is now, a little reflectivity at Cleveland coming off of Lake Erie again, those cloud streets. If you were to look at velocity, if it comes back here, yeah. Notice that velocity is 0 when the wind is coming across directly at the radar, which would be this direction. And so this wind is coming from the northwest to the southeast here. So guess what? It's coming across Lake Erie and forming snow around the eastern side of Cleveland here. The final thing, if you looked at dual pole and the precipitation type, yeah, it can detect precipitation type with this. You would expect most of this to be some form of snow, maybe dry snow, maybe wet snow. And yep, that's what you get, a lot of dry snow in here. Some ice crystals in this part of the cloud, maybe not reaching the ground. So all of this information coming out of radar is really helpful in determining precipitation, how the clouds are moving and all. So if you have any questions this week, please don't hesitate to ask.